Hello everybody, we're going to be reviewing this paper, Black Hole Event Horizons Are Cosmologically Coupled. It's 5 pages long, it came out about 6 days ago. Let's see what it has to say. So, let's start with the abstract. It is shown that an exactly static black hole event horizon cannot be embedded in a time-dependent geometry. Okay. So an exactly static black hole event horizon would be an event horizon around a black hole that is completely unchanging in time. And a time-dependent geometry is a space-time that changes with time. So far, so good. Forcing it to do so results in a naked null singularity at the would-be horizon. So we'll talk about what a naked singularity is, but a naked singularity is roughly a singularity that's not protected by an event horizon. Therefore, since the universe is expanding, black holes must couple to the cosmological expansion, which was suggested as the growth mechanism for supermassive black holes and galaxies, with implications for the dark energy puzzle. This last sentence is pure speculation. We'll see what they have to say about it. It's based off of a paper that came out 8 months ago, but we'll get there. Let's actually look through their computations to begin with. So let's start from the top and jump right in. For those of you who are just joining us, we are reading this paper, Black Hole Event Horizons Are Cosmologically Coupled. This paper came out of Bishop's University and the Trento Institute for Fundamental Physics and Applications in Italy. It came out about a week ago. So let's get started. So they say, let's zoom in on the columns. So they say that a major problem of contemporary astrophysics consists of the fact that supermassive black holes at the centers of galaxies must have grown very fast, which is problematic if one invokes standard astrophysical channels. So this is a well-known problem. It's how fast can you get black holes to grow to get to the size that they are today, because some of them are very, very big. Moreover, LIGO detections of gravitational waves from binary mergers involving black holes highlight the presence of stellar mass black holes in the mass gap where they should not exist according to well-established models of stellar evolution. So the idea is that you have a mass gap between supermassive black holes. These are things at the center of galaxies that are 1 million to 1 billion stellar masses, which is a stellar mass is the mass of the sun. And then you have solar mass black holes. These are black holes somewhere anywhere from 1 to 20 times the size of the sun in mass. But there's kind of a gap. There's a gap between the ultra supermassive black holes and the stellar mass black holes, and we don't really know how we go from one to the other. We don't know what's in between. So there's an issue that we're detecting black holes colliding with each other that are in between. So there's something weird going on, so presumably they're going to talk about that. These astrophysical puzzles can potentially be resolved if black holes interact with the universe in which they are embedded and their masses evolve over cosmological time. This is called cosmological coupling. Now, they go on to say, realistic black holes are not asymptotically flat, but are embedded in the universe. Well, that's true. It's when we typically think of black holes on when you're learning about them in a relativity course, the first thing that you do is you just study a black hole isolated from the rest of the universe. There's nothing else in the universe but the black hole, and you study that. But like they're saying, realistic black holes, they have other stuff going on around them. The study of astrophysical black holes usually neglects the cosmic expansion due to the vast separation between astrophysical, local scales, and the cosmological scale. All they're saying is that on the scale of black holes are, a few solar masses, they're smaller than galaxies, and the expansion of the universe occurs on the scale of billions or millions of light years. So there's a huge difference. We can probably just assume that the cosmological scale is irrelevant for astrophysics, the astrophysics of black holes. But maybe that's a wrong assumption. And by the way, yes, everybody does have access. Just type in this number into Google, you'll find the paper. Just type in archive 2407.14549, and you'll find the paper. Freely available, everything. So they say, however, over billions of years, tiny interactions between black hole and the surrounding universe, if present, accumulate and can become important. Okay. The recent reference 6 reports the observation of cosmological coupling between the masses of supermassive black holes and the scale factor of the Friedmann Lemaitre, Robertson, Walker universe. This was that paper I was talking about where they said that, oh, maybe dark energy is linked to black hole or supermassive black holes, which I'm a little bit skeptical of, but they're working on it. Oh, you can't see it? Here it is. 2407.14549 V1. Just type that into Google, you'll be fine. Right, so the observation that they're reporting was obtained from data of black hole populations in red elliptical galaxies in the redshift range 0 to 2.5 in the redshift value. This just means that it's roughly 5 billion light years away, so they looked at galaxies anywhere from 0 to 5 billion light years away. Furthermore, if black holes are non-singular objects with de Sitter-like macroscopic cores, so this is suggesting, well, what if the black hole doesn't have a singularity, maybe it has something else going on inside, then they could even explain dark energy, which would effectively be relegated to the interiors of the black holes. A phenomenology possibly extending to non-singular black hole mimickers, which are now the subject of a vast theoretical literature. So this is speculation here, but I think that what they're going to try to say is that black holes have to be growing because space-time is expanding. So they're going to try to justify some of this. Cosmological coupling is also in agreement with the recent DESI results of the redshift evolution of the dark energy equation state. Now that's fascinating. I hadn't considered that. I've mentioned the DESI results, that the dark energy equation of state is changing, which seems to suggest dark energy is getting weaker. And they're saying that their cosmological coupling is in agreement with that notion. So that's really neat. The 2023 tentative observation of cosmological coupling caused a lively debate in both the observation and theoretical communities during the past year, as the arguments supporting it seemed unconvincing to some of its critics. Here we provide more convincing ones. So I was one of the critics. I wasn't super convinced of it, but we'll see if their arguments are more convincing. So another context in which black holes can potentially interact with their cosmological surroundings is given by primordial black holes in the early universe, in which the Hubble scale is small, and the separation between black hole and cosmological scales may not be sharp. Right, so in the earlier universe, the universe wasn't as big, so the cosmological scale was smaller, which means the black holes could have a larger influence on cosmology and vice versa. Reference 11 pointed out the inadequacy of the Schwarzschild metric, or Kerr metric, to describe primordial black holes. So they're saying, I don't actually know what this paper is. Let's go take a look. I don't recognize any of the authors, but they're basically saying that the standard models that we use to describe black holes don't work when you're talking about very, very early black holes. Although the analysis relied on the specific Fikerta solution of the Einstein equations that ultimately turns out not to describe a black hole, its main point remains. Okay, so they say that there's some non-black hole discussions in that paper, but the point still remains that you can't use a Schwarzschild description in order to describe black holes in the early universe, which is fine. Now, I don't know what this sentence means. The problem of principle of describing a black hole or other strong field object immersed in an FLRW universe. Remember, FLRW is Friedmann, Lemaitre, Robertson, Walker universe. That's an expanding universe that kind of describes what we live in. Immersed in an FLRW universe has a long history dating back to McVitie and Einstein and Strauss. There's a review of the relevant solutions. Only recently, however, cosmological coupling, independent of accretion or mergers, has been included in realistic astrophysics. So what they're saying is, even if stuff isn't falling in, there may be some association between the expansion of the universe and the black holes themselves. So that's what we have to take into account here. In spite of the extremely interesting potential implications, the cosmological coupling of black holes does not yet have solid theoretical foundations, at least locally, nor it is backed by exact solutions of the Einstein equations, possessing all of the desirable properties for coupling, although progress was made in this direction. So they're saying that the arguments that have been made are kind of approximate arguments or heuristic arguments, because we don't have exact solutions that describe a black hole embedded in a cosmological spacetime, which is a little bit suspicious because we do have Schwarzschild de Sitter. And, well, I guess de Sitter spacetimes are not actually the same thing as FLRW spacetimes, but they're quite close. So let's see what they have to say about this. Perhaps we'll talk about it later. The possibility that black holes coupled to the cosmological expansion and that this coupling has even been observed has triggered a debate in the community. Fine. Critics point to exact coupled solutions without any mass growth, such as the Schwarzschild de Sitter. Ah, that's what I just said. See, I know what I'm talking about. Cutler solution, okay. A counter-argument is that being general relativity is a non-linear theory, the solutions of its initial boundary value problems are not always unique. Yeah, that is true. That is generally a true statement. To address this issue, here we turn around the question and ask whether an exactly static black hole event horizon, a null surface, and a causal boundary can be embedded in an FLRW universe. Let's take a look at what that footnote says. Because it is locally static, we exclude the de Sitter universe from our discussion. Indeed, the Schwarzschild de Sitter-Cutler solution is locally static and contains a black hole event horizon, but is irrelevant to the problem addressed here. So they're kind of shoving aside the objection that I just raised, the Schwarzschild de Sitter solution, even though that is technically an expanding spacetime with a static black hole in it. They're saying, well, it's locally static. Now, when they say locally static, what that really means is they're saying something like, if you only look at a small region, it looks like it's not changing at all, which is true. But if you look at the whole spacetime, you do notice that it does change. So they're concerned with locally changing universes, which is perhaps a reasonable thing to do. Interestingly, this question was raised in 22. I don't know what that paper is, but we're going to ignore it for now. When no one was yet to talk about cosmological coupling seriously, taking cosmological coupling seriously. These authors assumed a solution of the Einstein equations that is spherically symmetric, time-dependent, meaning not static, and is sourced by a perfect fluid with linear barotropic equation of state. Basically, that just means that the pressure just depends in a linear way on the energy. So the more energy you have, the more pressure you have, and that affects the way gravity behaves. Answering the question negatively through a perturbative analysis. So they found a negative, meaning that these authors seem to have found that you cannot have a static black hole in an expanding universe. Fine. Here, we generalize significantly this result. Okay, so they're basically taking the work of 22 and generalizing it. Fine. By studying the existence of an exactly static black hole horizon in a generic time-dependent geometry and provide several no-go arguments. Okay, now, interestingly, they don't use the word theorems, meaning that they're not going to make rigorous mathematical proofs. They're going to make arguments, probably heuristic arguments. That's okay, though. Why is it not interesting if locally static? It is interesting if it's locally static, but it's just there's an example of a locally static universe, locally static expanding universe with black holes. And our universe is not really locally static either. So anyway, in particular, we do not assume the Einstein equations nor specific forms of matter, but we rely only on the near horizon expansion well established in black hole physics. So they're not going to make any assumptions about how gravity behaves. They're not going to make any assumptions about the distribution of matter. They're just going to look at some so-called near horizon expansions. That I'll have to familiarize myself with, but if this is a well-written paper, they'll do the explanation for us. We find that embedding an exactly static black hole horizon in a time-dependent geometry turns it into a naked null singularity, providing theoretical support for cosmological coupling. So the conclusion that they're going to come to is that if you tried to have a static black hole in a universe that is expanding, or in general that is just changing, that black hole's event horizon degenerates to become a singularity itself. So there is no black hole. There's just a singularity. And that's probably forbidden due to things like the cosmological censorship hypothesis. So they're going to say this is a justification for why we think that exactly static black hole horizons don't exist, and they have to couple with the expanding universe. Okay, so now they're just going to describe what they're going to do. The next section sets up the description of an exactly static black hole event horizon in a time-dependent geometry, while the following sections show how this assumption leads to absurdities. So they're going to do a proof by contradiction. Specifically, section 3 shows that null and time-like radial geodesics, which I'll explain what they are when we get there, are incomplete at the would-be static horizon, where the Ricci scalar also diverges. I'll explain what that is as well. By the way, Kerr black holes are stationary, not static. So that's a separate thing. This static horizon must coincide with a naked spacetime singularity at a finite proper radius. Yeah, okay. So, yeah, that's fine. In section 4, we analyze the propagation of a test scalar field which exhibits divergences at the would-be static horizon. Section 5 assumes the FLRW background and argues that the static would-be horizon leads to paradox for the Hawking temperature, while section 6 contains the conclusions. Okay, so they're basically going to just provide a whole bunch of different arguments that show that you're going to get a singularity rather than event horizon where the event horizon would have been. That's the structure here. So, first, we're just going to go over some geometry. Static black hole event horizon in a time-dependent metric. Let's set up the description of a static black hole event horizon embedded in a time-dependent background geometry, which, remembering the origin of our problem, can be thought of as an FLRW universe. So, Ian, not today. You can DM me and I'll answer it later. So the idea is that they're basically just going to plop down a time-dependent background geometry, and then they're just going to see if they can build a static black hole there. However, we do not make this assumption until section 5. Okay, that's fair. And the time-dependent metric is general except for being spherically symmetric. Fine, okay. We do not want to commit to any exact solution of the Einstein equations or of the field equations of other theories of gravity because these are ad hoc and only a handful of them are known anyway. Okay, so this is actually, they're doing something very, 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 very broad. Namely that they are going to not even consider the dynamics, they're just going to think about the geometry, which is fine. In fact, we do not even assume the Einstein equations. Sure. Without loss of generality, a spherically symmetric and time-dependent line element can be written in this form. Now, I have to explain what all these symbols mean. So, this ds squared on the left-hand side, that's roughly the c squared of the Pythagorean theorem. So remember the Pythagorean theorem? You have a squared plus b squared equals c squared. That's what this formula is. This is the space-time equivalent of a squared plus b squared equals c squared. This is the space-time length of the hypotenuse. And then we have the contribution coming from time, because it's space and time. The time component always comes with a negative sign. That's important. And then you have the space piece. This is the a squared, if you will. So here they're saying that the space part is spherically symmetric. That's why this term is written this way. This is the metric. What we're talking about here, by the way, is a metric. This is the metric of a sphere, of a three-dimensional volume. And then they're just saying, well, imagine that that three-dimensional volume depends on both the radius and time. And then they're saying that the contribution of the time component to the space-time interval, to this c squared, the time component to the c squared, also has some time and radius dependence. So this is just a very general thing. There's two different general functions. You have t, capital T, and little a. In isotropic coordinates, that's what it means when they say that this is the isotropic coordinates here. Fine. And then they're also telling us that d omega squared, that's just the amount of the length that is contributed to by angles. So if you are at different angular positions on a sphere, then there will be some distance between you because of that. Don't worry too much about this. This is the line element on the unit 2 sphere. And the areal radius, this is actually important. The areal radius, so this is the area that corresponds, or this is the radius that corresponds to the area. So you can relate the area of a sphere to the radius of a sphere by a particular coordinate. And that's what this capital R is. This capital R is the effective radius of it's the effective radius of a particular chunk of spacetime. And notice that it's scaled, by the way. It's scaled by this function little a. The reason why it's scaled is because the spacetime itself is curving. So you might have more or less radius depending on the curvature of spacetime. So this can be read off at the angular part of the line element. So that's just this part times the r squared. And then you take the square root to get the radius. Fine. Jumped over here. The equation locating the apparent horizons, this equation generalizes the well-known relation locating the Schwarzschild event horizon, GRR equals nabla r. They're basically just taking the length of the vector that points in the direction of increasing radius. That's actually equal to 0 at the event horizon. This is a differential geometry fact, but basically, if you have a function r is a function, it tells you the effective radius that you're at a given position in spacetime. if you draw an arrow in the direction of increasing r, capital R, and then square that to find the length of that arrow, you'll find that that arrow reaches 0 length when you're on an event horizon. So that's what they're doing here. They're saying that this equation locates apparent horizons. That's what they're going to try to argue, that that apparent horizon becomes the singularity. So a single root corresponds to a black hole or white hole horizon. That's exactly what I just said. And a double root to a wormhole. Don't take that seriously. We're not talking about real wormholes here. This equation locates also event horizons and gives, well, this is the equation. So if you expand out this formula, you get this formula here. So the G upper TT, well, you'd have to go back and look at this formula here. This is actually a matrix. So you can write this as a matrix with minus t squared in the upper left-hand corner of the matrix. It's a 4x4 matrix. And then you have a squared in the 2, 2 component. And then you have a squared r squared in the 3, 3 component. And a squared r squared sine squared theta in the 4, 4 component. So then you take the inverse of that matrix, and you can write out this formula expanded in terms of GTT, which is the first, the 1, 1 component of the inverse of that matrix, and GRR, which is the 2, 2 component of the inverse of that matrix. Or put another way, you just have GTT is 1 over t squared, and GRR is 1 over a squared. So you get this formula. This is the formula that's going to locate where the event horizon is. So, oh, and by the way, r dot, this is just the time derivative of the areal radius. So if you have a function that tells you where your radius is, if you increase in time, how does the areal radius change? Because it could change in time, because space-time depends on space and time. And this r prime, this is the derivative of the areal radius with respect to coordinate radius r. So if you move around in space, it'll tell you how the areal radius changes. So that's what we're talking about so far. So this is our equation. Now, equation 2.3 is obtained also by imposing that a spherical surface of radius r be null. Okay, this is an equivalent thing. Basically, you're just asking, when is it that light becomes trapped on a sphere of radius r? That's equivalent to this equation here. Indeed, it is well known that static apparent horizons coincide with null event horizons. Okay, so they're going to try to impose static apparent horizons so that you get a null event horizon, an unchanging event horizon for a black hole. So they're basically going to try to show that solutions to this equation, the values of r where this is true, are going to be singularities. That's going to be the goal here. So the two-dimensional metric induced on the surface r equals constant. So now imagine that you have like a, so remember, r tells you basically how far you are away from the center of the spacetime in some sort of kind of rescaled way. So for a given value of capital R, that basically corresponds to a sphere, right? You have a sphere is a certain distance away from the center. And so they're saying that the two-dimensional metric, meaning like how curved, or what are they saying? They're saying that the two-dimensional metric on that sphere of constant radius r is static, but the time-dimensional, so if you basically look at how the geometry on the sphere behaves, it just behaves like a normal sphere. It doesn't change with time. But the time-dependent geometry just outside the horizon has t equals t of t and r, and a equals a of t and r, and the areal radius, r of t and r, varies in time and cannot match r equals constant on the would-be horizon. So what they're saying is that what is the argument that they're making here? So they're saying that the two-dimensional metric induced on the surface r equals constant is static, fine. But then they're also saying that if you're just outside of the horizon at the value of r where this equation is solved, they're saying that t and a, I see what they're saying. They're saying that this equation is changing with time, obviously, because t and a both change with time. And the areal radius also changes in time. And so the horizon cannot match a two-dimensional sphere, because if it did, then it would not be changing in time. But it has to be changing in time because it has explicit time dependence. I think that that's what they're trying to say. It's not super clear what they're trying to say, but I think that that's what they're saying. They therefore say the junction conditions cannot be satisfied there. The discontinuity in the metric induced on this two-surface cannot be handled with distributional techniques, and the jump in the metric GAB, unlike a jump in its transversal derivative, interpreted as due to a matter layer on a null shell, has no physical interpretation. All right, maybe they'll explain more about that in a minute. We'll see what they have to say. All right, so let's keep reading. If not, then we'll come back to it and think about it. Okay, so now they're going to examine radial geodesics and the Ricci scalars at the horizon. So let us examine outgoing and ingoing radial null geodesics. Now I should explain what those are. I can go to the references cited, but this is just the Israel junction. Yeah, this is the Israel jump conditions here. And then here, what else do they have? They have, yeah, so 23 and 24 are just the junction conditions, which are fairly standard. Basically, it just means that on any surface in a smooth spacetime, you'll have that like one side of the horizon matches the other side of the other side of the horizon. Yes, this is new. This came out about a week ago. Right. So in outgoing, so I should explain what a null geodesic is. So a null geodesic is just any path that a light ray can take. So a light ray, it travels equally through time and space because the way that we define the rate at which you travel through time, or the way that we define, the way that we compare space and time is by a conversion factor of c. And so a null geodesic is just exactly the path that a light ray will travel. Now a radial null geodesic is just a null geodesic. It's a light ray. It's the path that a light ray would travel if it was going out from the center. And then you have outgoing and ingoing. So you could have it coming in towards the center, or you could have it going out away from the center. We will show that they cannot be continued inside the would-be static black hole horizon, which is unphysical. Okay, so what they're going to say is that these geodesics, if you try to have them come in, they have to stop. They can't continue, which would be a sign of a singularity. It's a sign of geodesic incompleteness. They're also going to say, furthermore, the Ricci scalar of the geometry diverges there. Okay, that's a cool claim. They're going to say that the curvature of spacetime itself becomes infinity at that static horizon. The difficulties arise from assuming an exactly static horizon in a time-dependent geometry, showing that this assumption is unphysical. So what they're saying is that the reason this happens is because they assumed that there was an exactly static horizon, and so we can't use that assumption. This is a proof by contradiction. So they're going to start with radial null geodesics. Consider a radial null geodesic parameterized by an affine parameter lambda. So this is just kind of like telling you how, this is just a number that tells you how far along the line you are. Like if lambda was twice as big, then you'd be twice as far along your light ray. And with a 4 tangent u, now I should explain what this notation means. So this is a vector, this symbol for a vector. Notice that it's like a parentheses. So this is the first component of the vector. It's the time component. The way that you know it's the time component is from this equation. So in this equation, you have that dt was the first coordinate here, and then you have dr, and then you have the angular coordinates. So if we go look over here, you have that this is the time component, this u0, and then this is the radial direction. So this is a purely radial null geodesic because you have time and you have the radial direction and nothing in the angular direction. So it's just either going in or out. Sorry, in or out. Now, the normalization, UC equals 0. What this means, by the way, this normalization, they're saying that this is a true statement about null geodesics always. If you have a null geodesic, that means that the contribution from the space direction, u1, is exactly canceled out from the contribution of the time direction. So it's traveling forward through time, but it's also traveling out or inwards through space. And if you look at this equation here, the time component contributes a negative sign, and the space component contributes a positive sign. And so for null geodesics, those are defined to be those geodesics or those light rays are defined to be such that the space and time pieces cancel out. So that's why they have this. That's why they have this normalization here. That's just always true about null geodesics. Geodesics being the straight line paths that light travels through curved spacetime. So they're basically going to expand this equation using what they know about the spacetime metric, which was over here. This is roughly the same as what they did here, by the way. It's just a slightly different formula, so the equation is slightly different. Here they have minus t squared u naught. Actually, we can probably read this off. So we can read this off here. So basically, replace the dt with u naught and replace the dr with u1. And then the left-hand side will be 0. So that's exactly what this formula is. We're just reading it off. Yielding the coordinate velocity of light rays. So then they're just going to solve this, I guess, for... oh, no, I'm sorry. That's not exactly what they're doing. They're writing u1 and... they're writing u1 as dr dt, essentially. U1 over u naught is dr dt because dr dt. This is the rate of change of the radial coordinate. And so then you can just solve for this and you get it's plus or minus t over a, depending on whether u naught and u1 are ingoing or outgoing. They say where the upper sign refers to outgoing, so it's dr dt, i.e. the radius is increasing with time if it's outgoing, so that's why you have a plus sign, and it's decreasing with time if it's ingoing. And this just tells you how quickly it's increasing or decreasing with time. The equation of, so zoom over here, the equation of these affinely parametrized geodesics, again, affinely parametrized just means that you have a parameter that runs along your null geodesic. These affinely parametrized geodesics, so this is an equation that describes affinely parametrized geodesics. This is called the geodesic equation, in fact. You take the derivative. This is basically f equals ma, by the way. So this is velocity. So you take the derivative of velocity with respect to time. So this is like acceleration. And then here's the gravitational force. So so this is acceleration, this is force. So this is the formula that tells you how the light behaves. By the way, so this first constraint equation, all it does is it gives you a constraint on one of these. So they have dr dt is t over a, and they're going to use that in this formula here. So then they're going to use 3.2, this formula, to find the time component of, so they're going to take, so this is, see the little a there? What this means is that there's actually 4 equations here. There's u0, u1, u2, and u3. Now u2 and u3 are both 0, so you don't have to worry about that. But u0 and u1 do matter, and so they have to solve for both of them. This is a system of differential equations. By the way, what's going on here, this is a combination, so you have various speeds being input here. That's what the u's are. And then there's this term gamma, this is a Greek letter gamma, which basically tells you how strong it's roughly how curvy the space is. It's not exactly that, but it's roughly that. Right, where were we? Right about here. So they're just going to try to solve this in the time component, which is the 0 component. So they just replace the a with a 0. And now they're just going to expand out this term. Now this term involves a sum over several terms. See how b and c are repeated? The fact that b is repeated means that you sum over b and you sum over c. So there would be a 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, and 1, 1, 1, 1. So you have to add up all of those contributions. Right, okay, so that's just the expansion that they did here. They know what u is, and then they rewrite this in terms of u naught squared. So this is just a differential equation that they can solve. They also need to know what these gammas are. You can figure out these gammas from this metric equation here. I'm not going to go over how to do that, but it's a thing that you can do. And the end result is you get the derivative of t and you get the derivative of a and in some combination. Don't worry about that. Yeah, we hate calculating Christoffel symbols. It's the worst. So then we're left with this differential equation. So now we have a differential equation for u naught, which is what we wanted, in terms of t and a, which is nice. And then they're going to do the same thing for the radial component of the, they're going to do the same thing for the radial component of the null geodesic velocity vector. They have to calculate more Christoffel symbols, that's what these gammas are, and they're going to get another differential equation for that radial geodesic. So they have two differential equations that they're going to need to know the answer to. I don't actually know if they're going to solve these differential equations, but let's look. Let's keep reading. Close to the static event horizon, the spherical geometry must resemble Schwarzschild, which, in isotropic coordinates, is well known to be approximated by the Rindler metric. Okay, so here's what they're doing. So they're saying if the event horizon is truly static, then when you're near the event horizon, maybe not when you're far, but when you're near the event horizon, the geometry there should be very, very similar to the geometry of a Schwarzschild black hole, because you're near the event horizon. And so like it's a very, very good approximation. And so we know that near the Schwarzschild black hole, we can approximate, like this is just this is an exercise in differential geometry. You can approximate in terms of you can approximate the geometry in terms of a constantly accelerating geometry. This is what the Rindler metric is. That's a constantly accelerating geometry. So you write that the metric, this is ds squared, this is the geometry near the black hole event horizon. This is equal to the constantly accelerating metric, that's what that subscript Rindler is, plus extra stuff, higher order terms. And the Rindler horizon looks like this. You have minus x squared over 4 dt, where x is related to the radial distance. I'll explain what that is in a minute. Plus 4 times m squared. M is the mass of the black hole. And then you have dx squared plus d omega squared 2. So notice that this term is the same because it's spherically symmetric. Go and look up here. You have dr squared plus r squared d omega squared. And here we, oh no, actually it's not the same. I'm sorry. This is very much not the same. Either that or they left out a typo. I'll actually, let's just double check. Let's just go double check what the Rindler metric is, because I don't think that's a typo. I don't want the Fermat metric. Is that a typo? We might have a version of it here. It's not usually written in spherical like. It might be a typo. Let's assume it's a typo. Maybe they'll let us. Maybe they'll explain why. Oh, did you see it? Did you see it? Where is it? Because I don't see a spherical like. Yeah, I don't see it. I mean, we could just trust them. Yeah, let's just trust them for now. It may or may not matter, because this is presumably they're just assuming spherical symmetry here. So it should just be, there should just be an x squared there. It's possible that there's a typo though. Right, okay. So x is related to m by this equation. So, sorry, x is related to r by this equation. So roughly the, if you increase x, then you increase r. It measures the radial distance to the black hole horizon. So if you have, I don't think that that'll actually play a role, but I hope it's not. I hope that typo isn't significant. So basically, x tells you how far away you are from the event horizon, rather than how far away you are from the center, right? So the horizon geometry is exactly static. So this is the near horizon geometry. They're saying the horizon geometry is exactly static. Hence, t dot equals a dot equals 0. Remember, dot is a derivative is the time derivative of a thing. And equation 3.6 approximates to, this is equation 3.6. So t dot and a dot are 0. So equation 3.6 should give us just that d lambda of 1 over u naught should be 2t prime over a with a plus or minus. There it is. d lambda on 1 over u naught is approximately plus or minus 2t prime over a. And by the way, what they're saying is that this is a static metric. And therefore, what's AH? They need to explain what AH. Oh, that's A at the horizon. Fine. And T, why are they? Yeah, and so they're saying that T prime is approximately 1. Why is T prime approximately 1? So T prime is this term, but that's not approximately 1. That doesn't check out. It's approximately a half, maybe. If we go look at what T prime is. Yeah, that's T. T prime is, I think that they define it. Where did they define it? Where did they define? Yeah, it's just d by dr. So here it's just d by, oh, no, I'm sorry. I'm very, very dumb. So T prime is approximately 1 because x has this factor of 1/2. And so if we look at so there's an extra factor of 2 that I would have missed, but it's fine. We're fine because d by dx is not d by dr. So d by dx and d by dr are not the same thing. But you can rewrite d by dx. You can rewrite d by dr, which is necessary in T prime, as d by dx once you write that dr is, m over 2 dx. So it's fine. Everything's fine. And so then this yields, you can just solve this differential equation. And you get that u naught is approximately a constant divided by lambda minus lambda naught, with c and lambda naught constants chosen so that u naught is positive and keeps the forward tangent future oriented. So they just want to make sure that you choose some constants so that the null geodesic still goes to the future rather than going to the past. So now here's the kicker, I guess. So either u naught goes to 0 as lambda goes to infinity, i.e. time stops, meaning that the light ray stops going forward into the future. So in some sense, the light ray just stops going into the future, which is very, very weird. This is if lambda is greater than lambda naught and c is greater than 0. Or else the radial null geodesic stops at a finite value of lambda naught, meaning that when lambda is equal to lambda naught, you get infinity. You get a divergence. Now that's bad. This is a signal of really bad behavior because this means that your null geodesic either stops moving forward in time, which is a sign of a singularity, or the null geodesic stops at some finite value along its geodesic path, which is also a sign of a singularity. So this is what they were getting at. Can't divide by 0, exactly. On the contrary, u1 is this. So u1 is totally well behaved. It just stops moving forward in space. The coordinate velocity tends to 0 as x goes to 0, 0 plus, i.e. the radial motion of light stops at the horizon. Oh, wait a minute, no. Okay, so ingoing radial null geodesics stop going inwards as they get closer and closer to the horizon, which is kind of strange. You'd think that they could just go in, right? And they can't leave the horizon if they are outgoing. The fact that ingoing radial photons cannot penetrate the static event horizon and fall into the black hole is unphysical. That's also a point. That's also like a really, really strange behavior, which indicates that something's going wrong here. This is super cool. The study of radial time-like geodesics gives similar results. Okay, I'll believe that. Generally, you can talk about radial time-like or radial null, and they're roughly going to be similarly behaved. Just so I can lay this out for you guys to make sure I'm explaining what's really happening. If you tried to shoot a light ray into this static black hole, directly into it, it would never get past the event horizon, even though it should just fall in. Something goes wrong with the geometry that stops the light ray from falling in. And by the way, the apparent typo, it doesn't matter at all for this conclusion. So, very, very, very strange. Which this is, I mean, like they could have stopped here and then said, aha, there's a singularity. But they're going to keep doing more to make a stronger case, which is reasonable, and I appreciate that they're doing that. All right, so they're also going to talk about the Ricci scalar. Now, the Ricci scalar is roughly a measure of how curved space-time is. So near a black hole, actually near a static black hole, the Ricci scalar is 0. However, you know, like anywhere where there's matter, the Ricci scalar is not 0. But if it's infinity, that's a sign of a singularity. Geodesic incompleteness is the signature of space-time singularities in the Hawking-Penrose singularity theorem, signaling the breakdown of space-time at the static horizon. That's what we just went over. However, the other common definition of space-time singularity, the divergence of curvature scalars, confirms this conclusion. So they're going to basically show that they're going to show that there's going to be even the other definition of the singularity also leads to the same conclusion. There we go. The Ricci scalar of the static geometry 2.1, the Ricci scalar of the static geometry 2.1, not to be confused with the areal radius r. Oh, this is a terrible use of notation. So they're using the Ricci scalar. They're using a curly r to denote the Ricci scalar. So you can just compute the Ricci scalar using the static geometry 2.1, which is this equation here. So this is not actually static, but it's the Ricci scalar of this spacetime with this geometry. You can just compute it. It's a bit of a mess of a formula, but this is what it is. It's all of this horrible stuff. However, they say because the horizon is exactly static, it must be that a dot equals 0 and t dot equals 0 in the limit that x goes to 0. So they take that limit where x goes to 0, and then they cancel out all of the a dots and the t dots, and you get this equation, that the Ricci scalar has all of these terms. Now, there's not really going to be a good intuition behind what these terms are. This is just algebra. They're taking this, they're taking a limit, they're throwing away some terms, and you're left with this. The first and last terms on the right-hand side of equation 3.12 are finite, and they can be neglected in comparison with the terms diverging as 1 over t. So we know that a, in the limit where x goes to 0, we've already established that, yeah, so in the limit where is it? Where were we? In the limit where x goes to 0, a is finite, so this term is well defined. T is finite, so this term is well defined. Actually, does t go to 0 in that limit? No, it doesn't necessarily go to 0. So I think that they'll get to that. We're just looking at which term, what the terms are. This term should be well defined. This term should be, yeah, I think that all these terms should be well defined actually, but we'll see. So they say definitely these two can be neglected because they're both finite. They are finite and can be neglected in comparison with the terms diverging as 1 over t. Okay, so they're saying that t actually goes to 0 in the limit where x goes to 0. Ah, okay, because they have that t is approximately x over 2. I see, they're getting that from here. So if you look at this formula, this term here, this x squared over 4, that is t squared. Go look at, reminder, that term in front of the first one is minus t squared. So if we have minus x squared over 4 dt squared, that term, x over 2, must be capital T. And then capital R is roughly 4m squared, or is roughly 2m. So A is just finite in the limit where x goes to 0. However, t goes as x over 2. And t prime is roughly 1, and t double prime is roughly 0 if you just take two derivatives of this t. So if you have t in the limit where x goes to 0, t goes to 0, and you're dividing by 0. And t double prime also goes to 0, but t prime goes to 1. So we'll see what happens here. A is not the FLRW scale factor. It's just a scale factor that depends on both space and time. Yeah, this is just the Ricci scalar of some particular metric with some approximations. True. So these are the. I don't actually know why they didn't neglect this term, but we'll see what they have to say. So denoting with RH and AH the finite values of R and A on the horizon, we obtain this. So we have, let's see if we can understand this. So we have minus 2a prime over a cubed, which is t prime is 1. That's this term. That's this first term here. They're just replacing t prime with 1. So they go from here to here. And then they have minus 4 t prime over a squared RT. That's this term here. And then they have the t double prime over a squared t. It looks like they actually are neglecting this third term here. They just probably forgot to write that because the third term is also finite. So, you know, it is what it is. So this is their approximation for the Ricci scalar. And then they say, well, actually, because it goes as 1 over t, notice that these two terms don't cancel out because t prime is about 0 and t double prime is about 1. Or, sorry, t double prime is about 0. T prime is about 1. These terms, they can't cancel. So this goes as approximately 1 over x, which goes to 0, or which goes to infinity as x goes to 0. And so they find that the Ricci scalar in this approximation is infinity, which is a problem. That's a singularity. And then they can also construct the Kretschmann and other curvature scalars and show that you also get singularities there. So how is this approximation derived? It's called the near horizon approximation. Roughly, basically, you just say that, look, the event horizon, any static event horizon is approximately this, plus higher order terms, which won't play a significant role, I don't think. But they should actually be careful about that. So I imagine that they probably were careful, but you know, take it with a grain of salt. Okay, so we have two proofs of a singularity showing up at the event horizon. Again, this is at the event horizon. This isn't like in the core of the black hole. This is a singularity at the edge of the event horizon, which is very, very weird, which means that there's a mistake, that something stopped making sense. So let's keep reading. Matter is also subject to divergences at the would-be static horizon. Let's consider a free massless test scalar field phi satisfying the Klein-Gordon equation. So let me explain what it's being said here. So they're saying that, look, you can imagine like throwing in matter. Now we're not going to assume that the matter has any gravitational effect. We're just going to see what does the matter do if you threw it into the black hole. Like what would happen? Well, there's an equation that tells you how matter behaves. In particular, this would be like the Higgs boson. So there's just an equation. It's called the Klein-Gordon equation. This box here, basically it means take two time derivatives and then subtract off two space derivatives. That's roughly what this is. However, the time and space derivatives vary depending on the curvature of spacetime, so it looks a little bit more complicated. But that's roughly what this equation is saying. In particular, they're interested in the near horizon propagation of the scalar field waves. This is the Greek letter phi. They're interested in the behavior of the scalar field near the black hole event horizon. And for simplicity, they're going to restrict it to S modes. So they're only going to allow it to be spherically symmetrical. So in the geometry 2.1, so that's the original geometry that we have, this scalar wave equation becomes this equation. So we have two time derivatives of the scalar field. We have two spatial derivatives of the scalar field, and then you have some cross terms because the space-time curvature is a little bit messy. And so this is the equation that it should satisfy. Now they're going to, okay, so I actually know what their plan is at this point. So they're basically saying, look, we have this formula, which is exactly true, but because the horizon is supposed to be static, we always can assume that a dot is 0, t dot is 0, and that t goes to 0 near the horizon. Those are reasonable assumptions if you assume that the horizon is static, that the black hole is static. And so what they're going to do is they're just going to take those assumptions and plug it into this formula. And then they're going to, so if you do that, if you assume that a dot and t dot are both 0, this term drops out, and t goes to 0 at the horizon. So this term drops out, and this term drops out. So you're just left with phi double dot equals 0 near the horizon. And so you get that, well, this just means that 2 time derivatives of the scalar field is 0. So there's only, there's a very simple solution that has 2 time derivatives being 0, which is just a constant plus a constant times the time. If you take 2 derivatives of this, I think everybody who's taken calculus follows this. If you take 2 derivatives of this thing, 2 time derivatives, you get 0. And importantly, as you take time to infinity, as you travel, upwards in time, this solution goes to infinity. I'm actually really suspect of this, because there's no guarantee that this scalar field is going to stay near the horizon as time goes to infinity, which would make this approximation significantly less accurate, which means that your behavior wouldn't necessarily diverge. This is probably the most suspicious thing that they've done. I'm not sure if this is actually convincing to me. The other calculations are fairly convincing, but I'm not sure if this is, but we'll keep reading. Their energy momentum tensor, so now they're just calculating the distribution of the energy and momentum of the system. Their energy momentum tensor, TAB, you can calculate it using this formula. This is just a known formula. It has a trace, so you can basically add up the total energy plus all of the momenta. And they find that also goes to infinity as you get closer and closer to the event horizon. And that's true even when you don't take the limit as little t goes to infinity. So you don't have to wait till infinite time later. The energy, the total stress energy of this field goes to infinity as you get closer to the event horizon. That's pretty believable, though. So what do they conclude? Well, they conclude that the free scalar field is equivalent to an effective perfect, this is more information. So they say the free scalar field is equivalent to an effective perfect fluid with stiff equation of state, effective energy density rho, effective pressure P, and trace. So this is a statement. The free scalar field is equivalent to an effective perfect fluid with stiff equation of state. So they're saying that you can model a free scalar field exactly as you would model a perfect fluid. So a perfect fluid is just an incompressible fluid in spacetime that doesn't interact with itself. And so if that's the case, then you actually can determine what the trace of the stress energy tensor is. It's the negative of the energy density plus 3 times the pressure. But they're saying that this diverges at the static horizon. However, the rho, since the energy density is this particular term, it's this particular part of the stress energy tensor, which is phi dot squared over 2, because this is finite, it must be that the pressure, so this term here is finite, but the whole thing diverges. So it must be that the pressure, the effective pressure diverges at the horizon. So that means that the pressure on the scalar field, that the pressure in the scalar field increases to infinity at the event horizon, which is, again, a contradiction. You can't have infinite density, except at perhaps a singularity, right? Or infinite pressure, rather. All right, now they're going to do another thing, this time about the Hawking radiation. We'll see where they go with this. Now, assume now that the time-dependent geometry is asymptotically FLRW, which means that it basically looks like our universe. We're going to assume that the background geometry is basically like our universe, describing an exactly static black hole horizon embedded in an FLRW universe. They're gonna take our universe and just plop down a static black hole horizon. Now they're gonna make some arguments about Hawking temperature, which is probably going to be very, very loose, but we'll see what they do. The Hawking temperature at the horizon is, well, it's TH is 1 over 8 pi m. This is a known result, especially true for static black hole horizons. The static black hole horizon just has a fixed temperature. It's a very simple formula, where m is the black hole mass. So the bigger the mass, the smaller the temperature. This is taken as the Misner-Sharp-Hernandez mass defined in spherical symmetry, which reduces to the Schwarzschild mass. Hold on one sec. TikTok's being dumb. So basically, this is the mass of the black hole, and they're defining it in a very rigorous way, which reduces to the Schwarzschild mass when you're spherically symmetric. And it must be constant for a black hole horizon to remain static. Oh, wait a minute. So how can you have Hawking radiation if your black hole is static? That sounds like a problem. The black hole must be in equilibrium with its Hawking radiation. That's the point. So if it's giving off Hawking radiation, it must also be gaining mass at exactly the same rate, otherwise it wouldn't be static. But the temperature of a photon gas in local thermal equilibrium, when decoupled from other cosmic fluids, is roughly the inverse of the scale, or scales as roughly t goes as 1 over a to maintain the black body distribution. Hopefully they'll explain more because that was very dense. To wit, a physical wavelength scales as the scale factor times the co-moving wavelength. Fine, co-moving is just the wavelength of the, well, it's just a set of coordinates that's kind of natural when you're talking about expanding space. Where lambda c is the co-moving wavelength, the frequency, this is just a standard result. To find the frequency of a light wave, you just take the speed of light, divide it by its wavelength, and you get that this is proportional to 1 over a, which is roughly the scale factor here, how much the universe is stretching. The Planck distribution of the spectral energy density, oh, they're doing some serious thermodynamics here. This is just a particular distribution for how electromagnetic energy is distributed kind of in a uniform way. It's called the Planck distribution. You can go learn about it in thermodynamics courses. And there's some constants here. We have h as the Planck constant. We have k is the Boltzmann constant. We have t as the temperature. We have nu as the wave, or nu as the frequency. And so this is the energy density at a given wavelength and temperature in the spectrum. This is only true. So this energy density is only preserved if the time scaling goes as 1 over the distance scaling. Okay, I don't know where they're going with this, but let's keep reading. Furthermore, the analysis of exact solutions of the Einstein equations representing black holes embedded in FLRW universes, which are usually described by dynamical apparent but not event horizons, yield black hole temperature scaling as t goes as 1 over 8 pi m a. So there's this extra factor of a in there. Notice that there's an extra factor of a in there as opposed to just no a here. Okay, this is kind of sus. This is the case for cosmological black hole solutions of the Einstein equations obtained by conformally transforming Schwarzschild, in particular to the Sultana-Dyer black hole, scrutinized in greater detail. Okay, it's not super relevant. At our would-be static horizon, it must be simultaneously, okay, yeah, this is the point. It must be simultaneously that the temperature is constant, meaning that it's 1 over 8 pi m, and that the temperature scales with the scale factor, or scales as 1 over the scale factor. They can't both be true. It can't be constant and not constant. So you have a contradiction. So, what's the conclusion? An exactly static black hole event horizon embedded in a time-dependent geometry 2.1 is, in reality, a naked null space-time singularity located at finite areal radius. All radial null, and so now they're just going to summarize. All radial null and time-like geodesics are future inextendable of this static horizon. That was the first piece of evidence that they gave us. Geodesic incompleteness defines space-time singularities in the Hawking-Penrose singularity theorems. Okay. If you believe Kerr, then you shouldn't believe that statement. But anyway, but this statement is a good one. The Ricci scalar also diverges at the would-be horizon. That's a sure sign of a singularity. A radially propagating test scalar field has divergent effective pressure there. So matter falling in would have an infinite pressure at the event horizon rather than at the center. Kind of weird. Finally, the Hawking temperature of a strictly static black hole horizon would have to be constant, while the expansion of the universe in which it is embedded dictates that it must scale like the inverse scale factor, which are incompatible requirements. That's also reasonable. I can summarize this roughly. So if the black hole is static, its temperature can't change, because otherwise it wouldn't be static. However, in order for its temperature to not change, the Hawking radiation it gives off must be matched by the temperature itself of the photons that are around it, just existing in spacetime. But the photons around it are decreasing in temperature because the spacetime is expanding. And so you have a gas that's expanding and getting less dense, so the temperature decreases. So the temperature should decrease, but the temperature should also stay the same, and that's a contradiction. So they say the analysis in 22 assumed the Einstein equations and a perfect fluid with linear barotropic equation of state as a source. Here we significantly generalized that result. We did not use any of these assumptions. Yeah, that's true. They didn't. That's really neat. Furthermore, we did not assume that the geometry is asymptotically FLRW, except in section 5, but only that it is time-dependent outside the static event horizon. Therefore, our result is quite general, including FLRW as a special case. Forcing an exactly static black hole event horizon onto a dynamic background turns this horizon into a naked null singularity. Preventing it from expanding, which can only be done with strong gravity objects since weak field objects will co-move, tears the spacetime. So, this is their conclusion. If you tried to put a static black hole into an expanding universe, Well, the black hole wants to expand, naturally wants to expand because the universe is expanding. So if instead you surround it by matter to keep it from expanding, by adding more gravitation pulling it inward to balance out the expansion of the universe outwards, that tears the space-time, and it creates a singularity at where the horizon would be, which is a really neat way of putting it. The problems described in the unavoidability of the naked null horizon arise from the assumption that the black hole horizon is exactly static and disappear if this assumption is dropped. Thus, time-dependent event horizons are possible. Finding their dependence on time or on the scale factor of the host FLRW universe presumably requires the complete specification of the geometry and commitment to specific metrics, and will be investigated in the near future. So, and then they have some, acknowledgments. Here are the references. So this was actually a pretty neat paper, in my opinion. I think that there are some things that probably should be double-checked. They should probably make some reasonable assumptions about the near-horizon geometry, because this is a pretty strong assumption that they're assuming that the near-horizon geometry doesn't adjust to, doesn't contribute to the Ricci scalar, and doesn't contribute to the radial null geodesics in a way that it actually kind of cancels the divergences. But I think that they're probably right about this, actually, especially because the physical intuition they give in the conclusion, this idea of tearing the space-time, when you, if you tried to keep a black hole static, is a really neat and compelling idea. So I'm going to give this paper a 9 out of 10. How about that? Oops. We're going to give this paper a 9 out of 10. Yeah, I hope everybody enjoyed. If you're interested in reading this paper, the archive link is here. So it is archive 2407.14549v1. It just came out 6 days ago. This is not published, by the way. This is like pre-publication. It's preprint. And the paper is called Black Hole Event Horizons Are Cosmologically Coupled by Valerio Faraoni and Massimiliano Rinaldi. So this seems like it's an Italian group. With that said, for everybody watching on YouTube, I hope you enjoyed.